All right, guys, so we are done just finding trig values and all that stuff that we've been doing the last couple weeks. We're going to start doing some graphing of the trig functions, which may seem kind of intimidating, but we're going to break it down into some nice, easy things to remember, some nice rules, and it's one of the areas that typically people do pretty well on is the graphing piece. So I think this will be something good for you guys, and it gives you some different way to think about trig functions. So just this first time, we won't always do this every time, but just to graph first, to get a sense of what the graph of sine looks like, I want to just fill in a table of charts. And again, we won't be doing this every time, but we're just going to do it this time just to get a sense of what this looks like. So what I have here, right, is the sine function, a table with the sine function, and a bunch of angle values. Okay. So you should know what the sine values are of all these angles are, but to save us some time, I'm going to help you fill them in. So sine of 0 would give me an output of 0. If I put an input of 30 degrees, I would get a sine value of 1/2. 60 degrees, I would get root 3 over 2. 90 degrees, I would get 1. 120, root 3 over 2. 150, I would get 1/2. 180, I get 0. 210, I get negative 1/2. 240, I get negative root 3 over 2. 270, I get negative 1. 300, I get negative root 3 over 2. 330, I get negative 1/2. And 360, I get 0. Okay, so again, these are all values I'm getting from my special triangles and my quadrantals, stuff you were tested on the other day. So this shouldn't be anything new for you. But all I did was just list them out in a chart. I want to get a sense of what these points look like graphically. So on the x-axis, I'm going to have my angle measure, right? Angle measure, which are all going to be in degrees. And again, on my y-axis, I'm going to have the ratios. And we know my ratios all lie between 1 and negative 1. And let's just make actually every box here, let's make it every 30 degrees. Now notice I didn't include the 45 degrees on here. I could have, but just to make things simpler and have them work out kind of nice, I didn't in this case, but you could. We're just trying to keep it as straightforward as possible. Our goal here, right, is just to get a sense of what does this graph of sine look like. Okay, so there's your graph of sine, or excuse me, your label of sine here. And the y-axis is already labeled. So let's actually just plot these points. I'm going to do it in a different color. Let's do green for GA. So I have 1 point, right, of 0, 0. So on my graph, I'll plot 0, 0. At 30 degrees, I have 1/2. So that's going to be halfway up. 60 degrees is root 3 over 2. That's pretty close to 1, but not quite. So it might be right there. And then at 90 degrees, I am at 1. Right after that, my graph starts going down. So 120 is root 3 over 2. It should be the same height as the point you made at 60 degrees. 150 is 1/2. And 180 is 0. Notice now after this, my net points start becoming negative. 210, I get negative 1/2. 240, negative root 3 over 2. 270, negative 1. 300, negative root 3 over 2. 330, negative 1/2, and 360, I'm back to 0. And you might know or suspect or remember that if I were to keep on going past this to 390, those values would just start to repeat. Okay, those values would just start to repeat. So it kind of looks cool. Now don't forget we can connect all these points. So let's see how good of a job I can do connecting it. Not my best, but not my worst. Oh, that wasn't good. Okay, but it should be a nice, smooth graph. And remember, if I were to keep on going, this graph would just start to repeat. Okay? So the actual graph of sine is this infinitely long, kind of wavy-looking, it's not a line, because it's not straight, wavy-looking graph that kind of goes up and down in between 1 and negative 1. Okay? Now notice that part I did in green was just one cycle around the circle, or what we call one period. Okay, and after that one period, the graph begins to repeat. Okay, notice I had one bump that went up and one bump that went down. After 360, I would repeat that up bump and go down, up, down, over and over. So the important thing to remember is that these graphs go on forever. However, we're only going to graph one cycle of them, or again, what we call one period. So I do want to point out a couple of things here. Characteristics of the sine curve. The curve is easily divided up into blank parts called quarter periods. Well, if it's quarter periods, you might guess that's 4 parts. So notice that if I were to divide the graph up into fourths, right? So notice I divided the graph up into 4 pieces. Notice at the beginning, right, of every fourth, I have a point at 0, a max point, a point at 0, a minimum point, and another point at 0. So notice that every one of those fourth points, okay, is a really kind of special point. It's one of the 0 points, or is one of those maxes and min points. We're going to come back to that, but that's a really important feature. Okay, talked about this already, but the period of the graph is how long it takes the graph to complete one cycle. Excuse me. So how long did it take to complete one cycle here? Well, it's 360 degrees. You'll notice that's the solid line in green. It's how long it takes for the graph to repeat. As we mentioned before, after that, the graph would start to repeat and look the same again. The period of this sine function, I just said it, is 360 degrees. That's how long it took to repeat one cycle. And then number 4, I mentioned this as well, the function continues on infinitely in both directions, really important point. But most of the time we will only graph one period. You do not, in fact I would not, do not put arrows at the end. You can just stop. So don't go like that at the end, because that would indicate then the graph is going up in that direction forever. And the sine function does not do that. So the way I would actually want you to graph it, okay, is to literally just stop there. You don't need to do anything else. I don't know why I did that. Maybe there's a time limit. Okay, you don't need to do the dotted part. Just stop at those endpoints. Okay. So if you go on to the next page, you can see a little bit more, probably a better computerized version of mine. Again, you can see that part highlighted in red is one period of the function. However, you can see the dotted portion that it does go on forever. Notice it highlighted the important quarter period points. The point where it started at 0, then the next quarter period point, the max, then another 0, then a minimum, then another 0. And these occurred at every fourth. Not every fourth point, but every fourth of the graph. So if you divide it up into fourths, you'll notice that at every fourth, there's kind of an important point. So some key points and stats. The period, some of these we've talked about. The period, 2 pi, oh boy. I'm going back to my pre-calc days. You'll come to that next year. The period is 360 degrees. Okay. Again, how long it takes to repeat. The max, what's the maximum value? The maximum y value is 1. Where does it occur? It occurs at 90 degrees. Notice if I were to keep on going, it would occur at 450. It would then occur again at 810, right? And again, notice the difference between all these points is 360, right? So every difference of 360, you're going to reach your max point again. Conversely, your minimum is -1. That occurs at 270, okay? I could put etc. on here, 270, 630, okay, etc. And notice again, I could go back in a negative direction as well. So it doesn't only mean positive angles. It looks like at -90 degrees, I would also have another minimum value. Okay, we don't always have to list that, but I just want you to be aware of it. Increasing, decreasing from, let's ignore that. Save ourselves a little time, ignore that. The y-intercept, in this case, was 0, 0. The domain, don't say the domain 0 to 360. It's actually negative infinity to infinity. It goes on forever. We just graph 0 to 360, but it does go on forever. The range, -1 to 1. Notice the roots in this case, okay? The roots are at 0. 0 degrees, 180, 360, and so on, right? Those go on forever in both directions, negative direction and positive direction. And notice also that your maxes and mins occur halfway between your x-intercepts. So if we go back up, and let's take a look at these 2 points, 180 and 360. What's halfway between them? 270, okay, right? Halfway between 180 and 360. That corresponds to a minimum value at 270. Same thing for 0 and 180. Let me switch colors. Let's go to yellow. At 0 and 180, halfway between 0 and 180 is 90, and I had a max point. So notice that your maxes and mins occur halfway between those points, those x-intercept points. And I just want to introduce one other concept to you guys. I'm going to draw this dotted line that cuts the graph in half. Notice that that dotted line cuts through all the x-intercepts here. We're going to call this the midline. And you can think about the midline as a line that cuts a graph in half. It's in the middle, right? It's perfectly between your maxes and your mins, right? It's your midline, which in this case, the equation of my midline would be y equals 0. So the midline on our sine graph is 0. Okay, it's where all those x-intercept points hit. And notice the maxes and mins, okay, are both one above and one below the midline. So perfectly kind of balanced, okay? All right, so let's actually get to some graphing. Okay, let's get to some graphing. And just to review some of our things, our function transformations, if I have a, some number a, times the function on the outside, that meant I multiplied, I spelled that wrong. Means I multiplied my y values by a. Okay, we've covered this before. This is just our function transformation rules. When I had a number outside the function being multiplied, it multiplied my y values by a. Adding or subtracting a number on the outside meant a vertical shift. So shift vertically plus or minus c, and then when it was plus or minus a number on the inside of the function, that meant shift horizontally. Shift horizontally, okay, plus or minus c, okay? So just a reminder of some of our function transformations, okay? So here is a question. We know what the sine graph looks like. My question to you now is, what would the graph of 3 times sine of a look like? What would it do to the graph? So let's actually check this out. So we're going to only graph one sine period. We're actually going to graph sine of x and 3 sine of x to maybe see how they compare on the same graph. All right, so I'm going to make a graph like this, and since I'm only doing positive values for right now, you can kind of make a lopsided graph like that. And I'm just going to plot the sine function. So I'm going to say my sine function is going to be in black. And I'm only going to plot those midline points, those x-intercepts, and the maxes and mins. So I know I have a point of 0, 0. I know I have a max point of 90, 1. And I have a point here of 180, 0. I know I have a min point. Okay, I have 270, -1, and then I have my last point of 360, 0. So this is my sine function that we already plotted. Again, we didn't, oh, that's a very squiggly line. Let's flatten that out. Notice we didn't plot all the points this time. You don't have to. We're only going to graph those maxes and mins and those midline points. Okay, so every fourth, right? Those quarter period points we talked about. So that's your sine graph. Let's see how 3 sine of x would compare. Let's do that in red. So now I'm going to compare 3 sine of x with that. So we said above here that if I have a number in front, all that's going to do is multiply my y values by that number. So let's take the point 0, 0. If I multiply that y value of 0 by 0, I still get 0. Thus my point on 3 sine of x would look the same. 90 comma 1, multiply that value by 3, and I'm going to get 90 comma 3 now. So that point's 90 comma 3. 180 comma 0, multiply 0 by 0, you still get the same point. 270 negative 1, I'm going to multiply that by negative 3. Just space this out a little better. Let me scroll down. That's going to become 270 comma negative 3. And then 360 stays the same. So when we think about this, what did that 3 do to my graph? It really kind of made it, stretched it out vertically, which really shouldn't be a surprise. We've kind of seen that a whole bunch of times this year. So 3 sine of x looked like it stretched that graph vertically. It multiplied all my y values by 3. So in this case, the 3 affects what we call the amplitude. Okay, the amplitude. That's the term we're going to use for the distance between the midline of the graph and the max and min point. So we didn't draw that dotted midline here, but the midline would be at 0. Okay, the midline here is still at 0. What's the distance between the midline and those maxes and min points? Notice that distance is 3, and this distance is also 3, right? So you can think of that number in front, that 3 or the a value, as the distance between the maxes and min points and the midline. Okay, I'm going to say, draw a little arrow here and say it always has to be positive. When we talk about the amplitude, amplitude's a distance, so it always must be positive, the amplitude. So just keep that in mind, and it's the distance between the midline and 0. So here's what I want you guys to do. I want you to hit pause, and I want you to try, or actually, we'll hit pause in a second. We'll fill in some information here first, and then I want you to see if you can graph y equals negative 2 sine of x, and then we'll come back and talk about it together. Okay, but let's first fill in the information. The amplitude, okay, we know is that number in front. We just saw it. We said it always has to be positive, though. So my amplitude's not going to be negative 2. It's going to be positive 2. The period, how long it takes to repeat, we know is just 360. The quarter period, how do we find those points, that the maxes and the mins? All we're going to do is we're going to take that 360 and multiply it by a 4th. And we're just going to plot every 90 degrees. Every 90 degrees, we're going to plot a new point, and you'll kind of see how that works. The midline, we know, is just 0. And we know we're going to start at 0, 0. We'll ignore the flipped for right now. So what I'm going to do is graph sine of x in black first. You're not always going to graph sine of x first, but just for the beginning right now, we will. Okay. And I'm going to show you how to use those quarter period points to help find the next point. So I know I got 0, 0. I'm going to add 90 degrees to 0 to get my next point of 90 degrees, comma 1, comma the max. I know I go from a midline to a max, back down to a midline. I'm going to add 90 again, or add the quarter period to 90 to get 180, comma 0. I'm going to add another 90 degrees to 180 and get 270. 270, comma 0, and then I'm going to add another 90 degrees and get 360, comma 0. All right. So since this is not really my graph, I'm going to make it dotted, because that's not really the answer to negative 2 sine of x. All right, so that was y equals sine of x. Now, in red, I'm going to graph y equals negative 2 sine of x, and what I'm going to do is apply those same rules as I did before. I'm going to take all my y values and multiply them by the number in front. So, or let me graph the midline first, and then we'll do that. So my midline here is at 0. Y equals 0. So I'm going to take my value of 0, 0, multiply it by negative 2. It's going to stay at 0, 0. 90, comma 1. If I take that 1 value and multiply it by negative 2, that actually makes it negative 2. So instead of being 91, my new point here is going to be 90 negative 2. Interesting. Notice I don't go up first here. I go down. 180 comma 0 stays at 180 comma 0. 0 times negative 2 is still 0. Oops, it looks like I made a mistake. On my original graph of 271, it should be 270, or 270 comma 0, it should be 270 negative 1. Sorry if that was worrying you before, 270 negative 1. If I multiply that negative 1 times negative 2, I get a positive 2. So that puts me up here. So that's 270 positive 2. And then the last value, 360, 0, is there. So notice what happened. Okay. My graph flipped. So notice over here where it says flipped. Yes, it is flipped. And why did it flip? It flipped because of that negative. That negative in front flipped it. Okay. Now, you might be saying, oh man, I got to flip these graphs. It's really kind of confusing. Well, let's take a look at a couple of characteristics and I'll kind of show you what's the easiest way to walk through these. So notice, again, that the difference between the min and the midline, again, is the amplitude. So that did not change, even though we had a negative. That distance between the max and the mins and the midline is still just the amplitude. But notice, on a normal graph, let's go back to the regular sine graph. I start on the midline, and normally I go up, and my next point is a max point. And I go max, I go from I started a midline, I go to a max. I go back down to the midline, then I go down to a min, and then I go up to the midline. So I have this pattern of midline, max, midline, min, midline. Just notice that pattern repeat. Midline, max, midline, min, midline. Okay? That's on a normal sine graph where there's no negative. What did the negative do? Instead of going up first to a max, I still started the same place. It still starts on the midline. But instead of going to a max first, I just went to a min first. And then I went back to the midline. Then I went to a max. And then I went to a midline. So just notice, instead of going to a max, I go to a min. But notice the amplitude was the same. So the way I would think about these graphs is determine the amplitude, okay, and then determine if it's flipped or not. And then all you have to worry about doing, let me just change colors here, blue, is if it's flipped down, instead of going up the amplitude, you're going to go down an amplitude of 2. Or if this had just been positive 2 sine of x, you would have just walked up an amplitude of 2. So if you remember those patterns, a normal pattern, on a regular sine function, you go to the max first. When it's flipped, you just go down to a min first. And you go down how far? Whatever the amplitude is. And again, that amplitude comes from the number in front of the sine function, and you can ignore the negative. We know what the negative does. The negative just makes you go down to a min first instead of a max. Okay? So I would count by quarter periods, which in this case right now is always going to be 90 degrees. So just keep counting by 90 degrees. Remember those patterns of midlines max or midlines mins, depending if it's been flipped or not. Make sure to draw in that dotted midline, in this case my green line of 0, because that's going to come into play a little bit later on. It's going to be helpful to draw it. And that's it. I didn't get quite as far as I wanted to in the video, but that's okay. Your only homework is problem number 2, graph y equals 4 sine of x, and then the next class we're going to start going a little bit quicker through some of the other things we can do to sine.